Hello, today we're going to talk about stoichiometry. First thing we need to talk about is mole ratios. So if you have a chemical equation like CH4 plus 2O2 yields CO2 plus 2H2O, the mole ratio refers to the ratio of the coefficients. So if I want to know the ratio of CH4 to O2, that's a 1 to 2 ratio because of the coefficients there. We can also use that as a fraction when we're reacting, when we're calculating for this chemical reaction. So if you have some amount of moles, you can use, let's say we have moles of CH4, we could use there's one CH4 for every 2 O2. As long as we have moles, we can use the coefficients there to cancel out the CH4 and change that into moles of oxygen. So that's why we call it a mole ratio, because the coefficients can be used when calculating with moles. Okay, we can also calculate with other quantities, but you have to convert it to moles first. So if you start with mass, you can convert it to moles using the molar mass. From the periodic table. If we have particles of any kind, so atoms or molecules or ions or formula units, we can use Avogadro's number, so 6.022 times 10 to the 23rd. If we have molarity, we can get to moles by using the volume in liters. And then, and this is for an aqueous solution, molarity of an aqueous solution. And then the last thing is, if you have the volume of a gas at STP, then you can use the molar volume of that gas. The molar volume of any gas at STP is 22.4 liters per mole, and we can use that to get to moles. So your strategy here is to whatever unit we're starting with, you want to convert it to moles. Then you can use a mole ratio, and then you can use these same things to get it back to the unit that you're looking for. So make sure you're following that strategy when we're doing stoichiometry. So let's do an example of stoichiometry. If we this question is asking how many molecules of oxygen gas can be produced by decomposing 1 gram of hydrogen peroxide according to the balanced equation. You'll always have a balanced equation, or you'll need to write a balanced equation when you're doing stoichiometry so we can have the mole ratio handy. So we'll start with that 1 gram of hydrogen peroxide. And you always want to change grams to moles using the molar mass. And hydrogen peroxide's molar mass is 34 grams per mole. Then once you have moles, you can use the mole ratio. There are 2 hydrogen peroxides in our balanced equation. And since we're looking for oxygen gas, I want to put the O2 on the top. And if you stop there, you'd have moles of oxygen gas. But we don't want moles, we want molecules. So this time I want to use Avogadro's number, 6.022 times 10 to the 23rd molecules in 1 mole. And I put the moles on the bottom, so that cancels. And if you do 1 divided by 34 divided by 2 times 6.022 times 10 to the 23rd, you can get the molecules, which is 8.86 times 10 to the 21st molecules of O2 gas, and 3 sig figs. I would avoid rounding until the very end so you get the correct number of significant digits. Okay, so let's talk about yield. We typically would say reactants yield products. So our theoretical yield is your calculated yield using stoichiometry. Theoretical is how much you would make if everything went absolutely perfect. So that your yield is always products, right? Theoretical yield is how much you would make in the perfect world. Actual yield is what you actually make in the lab. Now, there's a lot of different reasons why your yield might not be 100%. Typically, it will be less than the predicted amount with what you're calculating. The only situation where you might have quote more is if you have some kind of contaminant added in, like excess water or something just extra in your solution. But that would be a different source of error that you'd have to consider for your lab. Typically, we're going to have less than 100% yields. So percent yield then is a measurement of how close you are with your actual yield to your theoretical yield. So percent yield is equal to the actual over the theoretical times 100. And if you divide and then multiply, then you get the percent yield. You can see how close you were. So let's do an example with this. It says, what is the percent yield of the following reaction? If reacting 46.1 grams of the cesium produces 28.3 grams of our product, which is the cesium oxide. So the first thing we need to do is calculate our theoretical yield. We have 46.1 grams of cesium. Grams, we need to change to moles using the molar mass. Grams per mole. Grams cancel. Then we can use a mole ratio. There are 4 cesiums used for every 2 of the cesium oxide. Cesiums cancel. And then we need to get it back to grams because our yield is given in grams here. I need to use the molar mass of the CS2O, which is 281.8 grams per mole. And moles cancel. And then when you multiply and divide, you get that your theoretical yield is 48.9 grams of the cesium oxide. So that's if the reaction went absolutely perfectly. Clearly it didn't go perfectly because we only made 28.3 grams in the lab. 28.3 grams is our actual over our theoretical, the 48.9. And then times 100, and that will give us our percent yield of 57.9%. So a little over half of what we should have made. Now the last part of this stoichiometry section is limiting versus excess reactants. So I'm going to bring you back to an example from a previous section where we had water being formed from hydrogen gas and oxygen gas. And the example had us with 4 molecules of each hydrogen gas and oxygen gas. Green is the oxygen gas and the dark blue is the hydrogen gas in this case. And it's going to be forming water molecules. Now, if I reacted according to the equation, I need to react 2 hydrogen molecules and 1 oxygen molecule each time. So I'm going to produce 2 water molecules with the first reaction, 2 water molecules with the second reaction, and then I have oxygen molecules left over because I ran out of hydrogen molecules to react. And so I'll have some oxygen molecules left over. So we didn't talk about this last time, but the hydrogen gas in this case is our limiting reactant or limiting reagent because it runs out before you can use up all of the other stuff. It's the one that runs out first. O2 is then called the excess reactant because we don't use it up. We wind up with extra of it at the end of the reaction. So that's kind of the difference there between limiting and excess. It's fairly simple to look at when you have a picture like this, but a lot of times we won't have pictures. We'll have amounts, so we'll need to calculate. A good clue when you're doing these types of questions, if they give you amounts of both reactants, that's your clue that you need to do the limiting reaction process to figure out which thing is your limiting. Okay, so this example pulls it all together. How many moles of excess reactant are left over when 50 milliliters of 0.250 molar iron 3 chloride is reacted with 50 milliliters of 0.25 molar sodium carbonate solution. Your first step is that you need to have this balanced chemical equation. Now this is a net ionic equation because it's only showing the species that are reacting. It's not showing the spectator ions, which are the chloride and the sodium ions in this case. But we have our balanced chemical equation there. So now your kind of clue that this is a limiting reactants problem is because they give you amounts of both reactants, but also because it's asking about excess reactants. So that's another clue there that you should be looking for the limiting reactant. Now when you're doing these, you should test both of the reactants and see which one will make less product, because that will limit your reaction. Now molarity is equal to moles per liter. So molarity times liters gives you moles. So let's go ahead and do that first. I have 0.05 liters of the 0.250 molar for the iron. I also have 0.05 liters times the 0.25 molar for the carbonate. And I went ahead and just used the ions. I got rid of the spectator ions because the spectator ones don't really matter for this reaction. So when you multiply, you'll get the moles there. And you get 0.0125 moles for each of those. Okay, now that we have the moles, we can use a mole ratio. There are 2 irons used for every one of our product, which is the iron 3 chloride, or I'm sorry, iron 3 carbonate. And so for that one, if it went perfectly, you would get 0.00625 moles of our product. For the carbonate, there are 3 carbonate ions used up for every one of our product. So for this one, we would get 0.00417 moles of product formed. So because the carbonate ion produces less product, the carbonate ion must be our limiting. Which means that our iron is our excess. I'll say that again. Whichever one makes less product is your limiting. Whichever one makes more product is your excess. Now, in reality, this amount will never be made because you'd run out of carbonate before that would happen. So this would be our theoretical yield of the product. That's how much could be formed at maximum if everything went perfectly. But we don't really need that number because it's asking about the excess reactant. So in order to find the excess reactant, I need to use my limiting. Okay. So for the limiting reactant, the one that gets used up, this many moles of carbonate, I'm going to go ahead and figure out how much of the excess reagent actually reacted. So there are 3 carbonate ions reacted for every 2 iron ions reacted. So if I do that, I get 0.00833 moles of the iron reacted. Now our last step here is we started with 0.0125 moles of iron. And when we were reacting it with the carbonate, 0.00833 moles of the iron were used up. So I'm going to subtract it out because the 0.00833 moles were used. They're gone. So I'm left with 0.00417 moles of ions left over at the end of the reaction. Now, because there's 1 iron in the compound, it's also equal to the moles of iron 3 carbonate. It did not specify if it wanted the amount of the whole product or the amount of just the ion, but it's the same in either case. So that is our final answer there.